All right, back from break. So these have been some pretty good examples that we've been looking at. These are really good examples, I'm going to say, kind of all of them. I have to say this picture with looking at your own nose threw me off for a bit, but once we turn that back into just our usual triangles that I've been using other places, then it's good to be able to go back and apply it actually. So. And then after seeing that, going back and going, oh yeah, I can see what the triangles are representing. Maybe this much of the person's nose. Let's see. I don't know that they got things scaled properly. No, they really didn't, huh? They really didn't. Okay, so again, this is an example where the drawings and the given information don't really match up. I needed to pay closer attention to that. I mean, I went ahead and just wrote up these solutions, not really paying attention, but yeah, this is, yeah, that's quite, so the object is definitely inside the focal length. Okay. So their drawing here doesn't work. Okay, so go with the solution that we've come up with. Okay, I wanted to talk a little bit. At this point, once you've done a few of these examples and you start to get some kind of experience of how these work, what usually happens, what a lot of students report is, I can't keep track of all the possibilities. You know, what would happen if... What happens if the object is inside the focal point? What happens if the object is outside the focal point? What happens if the object is outside the center of curvature? What are all the possibilities of everything that could possibly happen if I move the object back and forth to different distances? And there are a set of graphs that you can work from. Now this is optional, you're not obligated to work from these, but what we can do is we can take this formula and we can actually plot the formula, assuming that we have a lens with some sort of a focal length, which is a fixed value. So I treat that as a constant. But what I'm going to do is I'm going to move the object back and forth. So that becomes the variable on the horizontal axis of my graph here. And then the DI will be wherever the DI is. When we treat DO as X and DI as Y and plot this function, what we get are some hyperbola. All right? And the hyperbola are lined up along a couple of asymptotes. And the asymptotes are, the vertical asymptote is at DO equals the focal length, and the horizontal asymptote is at DI equals the focal length. And what that does is it divides, it shows all the possibilities. So there are 4 quadrants on my graph. The first quadrant would be where we have DO positive and DI positive. In other words, that would be an example of a real object forming a real image. And it says, as long as the object distance is greater than the focal length, I will get a real object forming a real image. That's the only possibility for that region. So, and then we can ask, well, what happens if I take the object, but I move it inside the focal point? Well, if I move it inside the focal point, I'm not getting a real value of DI from that. I am going to get a negative value of DI, and that means that I'm down in this lower quadrant, and that's where real objects are forming virtual images. So again, these are hyperbola. I don't know if you've seen those particular functions used in this manner, but the key feature here is we've got these asymptotes, and if you get the asymptotes placed at the DO equals focal length and DI equals focal length, and you draw these solutions, then those are all the possible solutions. Now, what we've been looking at right now is the graph for converging mirrors and converging lenses. So yes, this also works for lenses as well as mirrors, because it's using the very same formula. So this quadrant is a real object forming a real image, and this quadrant is a real object forming a virtual image. And we can see what are the possible values of DI. Now look, as you bring the object closer and closer to the mirror itself, the image is headed off towards, or the image rather, when you bring it just past the focal point, is out at negative infinity, and then as you bring it closer to the mirror, the image distance also comes into it. So you can see all these correlations. It's too much for me to remember, and that's why I use the graphs. Because every time I encounter a problem, what I do is I go back to the graphs and I go, now where on the graph am I looking? Now what we also have here are virtual objects. And we said that, not so much in this chapter, when we get to the next chapter on lenses, it's not uncommon to have problems where we maybe have 2 or 3 lenses, one right after the other. And in that case, the image from lens number 1 becomes the object for lens number 2. The image from lens number 2 becomes the object for lens number 3. And that means that you could have object distances that are negative. You could have virtual objects. And in that case, we can also look and see what the solutions are. So converging lenses, everything can happen, except I can't go from virtual to virtual, because it's a converging lens. Now, to show the very same sorts of graphs, these are the 4 possibilities up here of object to image. To see what happens with a diverging mirror, or a diverging lens, the asymptotes in this case are on the other side because the focal lengths are negative. All right? So converging lenses have positive focal lengths, diverging lenses and mirrors have negative focal lengths, and the graphs just, what is it they've done? They've flipped over this way, something. It's the mirror image of the graph over some kind of a diagonal right there. So in this case, if I have a diverging mirror or lens, a real object cannot form a real image. Real objects can only form virtual images, and this is showing all the possible solutions. So anyway, if this is useful, go ahead and use it. If you play around with it and you find out it's not, don't worry about it. You don't have to work from these in order to solve things, but if you do play around with them a little bit, you may find that they're really handy. Okay, getting back to some of the slides here. For a convex mirror, the image is always virtual if the object is real. And the image will be virtual, upright, and smaller. Perfect example here. All right, so what we're going to do is, this is now convex, where it's a diverging mirror. And see, there are no solutions. There is no way. If it's a diverging mirror, and the light coming in is already spreading out, the mirror is just going to spread it out more. So there's no way that a diverging mirror is going to bring the light back together. So it's always going to be, the image is always going to be virtual. And what we can see is that the DI will always be less than the DO, and that will give us an image that's smaller. Okay, so everything they're talking about here, we can see from the graph. Okay, and rather than a whole series of statements of what's possible and what's not possible, we can kind of stare at the graph and I hope and figure all those things out. That's what I end up depending on. Okay, and so they've, it's a nice diagram they've put in here. I hope. I better check and make sure the diagrams match after these last couple of examples. So what we've done here is, it's diverging. So this is good to look at. So this is a diverging mirror. Here is the parallel light coming in. And since it's diverging, the light coming off is going to be spreading out. That's not going to come together on this side. The focal point is going to be a virtual focal point on the other side of the mirror. So we assign the focal length a negative sign. We give it a negative value to let us know that the focal point is here and not over here. And mathematically that works. It works in our formulas. And so what we can do now, let's do that first path where we come in parallel. We hit the mirror, and we don't go through the mirror, through the focal point. We reflect away from the mirror as if that reflection is coming right along the path from the focal point. So we're still using the focal point to align the drawing. Now what they're doing is they're using path number 3, which goes back to the center. That works. And so what they're doing is showing that the two paths coming away from the mirror, they're spreading out. Okay, so we're not going to get a real image from this. But when I do the dash lines back to the focal point of the center of curvature, they cross right there, and that's the location of the image. And that tells us the image it's not inverted, it's right side up, there's no inversion taking place. And these are the DOs and the DIs. I should mention this too. So in a number of these drawings, this is another incidence of this. In some of these drawings, they've drawn a picture of a person's eye looking at the light coming back out. And I think that can be really confusing. So I don't know if I would suggest thinking in terms of drawing the eye there. I almost feel like I should have maybe edited this and taken that out. First thing to remind yourself is human vision works so that an image, if I'm looking at an image, the image needs to be at least 25 centimeters away if you've got normal vision. The image needs to be 25 centimeters away in order for your eye to focus on it. So your eye actually wouldn't be able to focus on that image unless, for the particular problem, we can show that the eye is 25 centimeters away. So sometimes in these diagrams, they just put the eye too close. So if I'm looking at something like this, I actually can't focus on it anyway. If having the eye there is helpful, that's fine. Now, the other thing to remember is we're not just looking at that path, we're looking at this path too. So there's a whole series of paths coming out. So the eye is kind of sampling what's going on along that path. Okay. Anyway, whichever appears to be working well for you, that's fine. This is just a list of all the things we've been talking about, kind of working back and forth between the diagram and the formulas, and then making sure that the diagram and the formulas agree. Here's another example that we're going to try with a convex rear view mirror. So here it is, here's this truck coming up on us. It says that this mirror has a radius of curvature of 16 meters. Now, a big radius of curvature means it doesn't have much curvature to it. It's just a slight curvature. But as you know, as drivers, when you're looking in that rear view mirror, it's got a little bit of curvature on it. It's a little bit convex. And what that does is it gives you a wider range of view. So that by making this a little convex, it gives you a wider range of what's behind you rather than just a narrow range, which is good. You want to be able to see all the lanes and both sides of the road. The downside of that is that it distorts your estimate of distance somewhat. So something to be aware of. So what we're going to do with this is let's just run the numbers. It's a convex mirror. It's going to be diverging. Here is the image. That apparently is the truck. They didn't give us an HO value, but I wrote that in. Now what they did give us is they gave us a DO. They said it's 10 meters behind you. So this is where your rear view mirror is located, your side mirror. And it says that the focal length of that is, well, it's going to be 1/2 R. R is negative 16, so the focal length's minus 8. So I've got the object on one side, but the focal point's over here on the other. It's a negative focal point. It's on the negative side of the mirror. All right, I can plug numbers in. What I'm getting for the DI is negative 4.44 meters. Let's see what the diagram looks like. I bring a parallel light into the mirror, and then I reflect it back away so that it lines up away from that focal point. And then what I can also do is, I like using the focal points. So I'm going to take the light as if it's going to run into the focal point. And if I do that, if I take light that is converging towards a focal point, a diverging lens will bring that back out parallel. So those are my two image paths. That's my image light. These are my object light. Object light is coming away from this point. The image light is coming away from here. So I use those dashed lines, identify where the image is located. It's going to be 4.4. So when I'm looking at the side mirror, it looks like the truck, well, that it has to do with magnification too, so this is not the whole story, but at least the location of the image is only 4.44 meters behind the mirror, on the other side of the mirror. Whereas the truck's 10 meters behind me, this image is only 4.44 meters away. And the magnification we're getting is also 0.444. And what you find out is if the magnification matches the ratio of DI and DO, you're going to end up judging the object to be roughly the same size anyway. So it's something, we've been looking at lateral magnification, and next chapter we'll look at something called angular magnification, and that's what really comes into play. So we're through with the mirror stuff. What we want to do is move on and talk about what happens when we have a transparent material and light passes through. So here is light coming in towards the surface of some water. An easy set of materials here to work from is to think about air and water, or maybe it's a lens. What we're doing is we're kind of headed towards a lens here. Here comes the light, and there's a reflected path. Some of the light reflects, but some of the light, if the material is transparent, will pass into the material. So as you know, if you shine a light on water, you do see a reflection off the surface, but you also can see some of the light goes into the water. Now the angle of the reflected portion matches the incident path. That hasn't changed. That's what we've been looking at with mirrors. But what we find is that the path going into the water does not travel at the same angle that the incident light did. The angles don't match. And then it comes down to the material properties. Well, what is it about the properties of water and the properties of air that are making the path of the light not go in a straight line? And you guys have seen the effects of this, right? You see, if you hold something underwater and you look at it, you go, that's not where it looks like it's located. I know it's located here, but it doesn't look like it. Or if you take a stick and put down in the water, it looks like it's bent at the surface of the water. So this effect is referred to as refraction. So this is refraction, and the light that's bent is referred to as the refracted path. So what's happening here is that light, photons of light, particles of light, interact with the molecules that they're passing through. When light's passing through air, when visible light passes through air, it doesn't really interact very well with the air molecules. So the absorption and the scattering is pretty minimal. When it goes through water, it interacts much more. So what happens is, even though the individual photons are traveling at light speed, they're traveling at c, when they interact with a molecule, it's kind of like they get absorbed and then re-emitted. And the process takes a little bit of time, and it slows down the progression of the light making its way through that material. So again, it's kind of like a relay done with photons all traveling at c, but the handoffs take a little bit of time. So the light going through the air is almost going at the speed of light in a vacuum, but in the water it's significantly reduced. We have a way of keeping track of that effect, or quantizing it. What we do is we define something. This is a little funny, but this is how we define it. We say that there is something called, for a material, the material's index of refraction. And the index of refraction is given by the speed of light in a vacuum divided by the speed at which light makes its way through this material. Now, for a vacuum, that ratio would be 1, but in air, interacting with those air molecules slows down the light. Now, at 1 atmosphere pressure and 0 Celsius, 273 Kelvin, The slowdown is not very significant. For most purposes, we can just treat this as 1, unless we're doing a really high precision calculation. So 1.003, but for water that effect is 1.33. So the speed of light, the speed at which a light beam makes its way through water is only about 75% of its speed in air. So it has slowed down significantly, and you can see for other materials, for glass this tends to be around 1.5. For diamond it's 2.2, so light really gets slowed down. When light's passing through diamond, it's only traveling at about 40% of its speed that it would have in a vacuum. So what this leads to is a bending. There's a bending that takes place as the light slows down. So very quickly what we can say is this. Let's imagine 2 parallel paths that the light is traveling. And so the 2 possible paths, the light's headed side by side, a couple of possible paths the light could take. What happens is that this light hits the surface first and slows down. This side keeps going fast. And as a result, that creates a bend. How many of you were in marching band in high school? So in marching band, I think it was a prerequisite for the class, right? In marching band, what you do is, you're marching down the street, everybody's lined up in their rows. How do you turn? And what you do is, if I want to turn to the right, I have the people on the right side slow down so that the people along the left columns can get out ahead, and then everybody can turn and move off in this new direction. And that's what happens with light. When we look at the way that particles propagate, when we use quantum mechanics, and look at the way that light propagates, photons of light, we find out that this path begins interacting, light along this path begins interacting with the water molecules more, slows down, and the result is it tips the entire path. So theta 2 does not equal theta 1, and the general rule here is as the index goes up, as the light interacts more and more with a material, when it enters a material where it interacts more, it slows down more, and its angle becomes less. And remember, these angles are measured with respect to the normal. Now, we can reverse this path. What we can do is start with the light in the water. Now, the theta 1 and the theta 2 will be related the very same way. But notice that if the light's starting in the water, the reflected path is within the water. So the reflected paths don't reverse, but the refracted paths do when we change that direction. And here's an example. What's happening here is this person waving to this other person. If you've seen things down in the water like this, so the light coming from this person's foot comes to the surface and then it bends, it refracts, and so the person looking says, oh, the portion of that person that's down in the water looks like it has shrunk significantly. You may have seen this as underestimating how deep something is. When you're looking at a swimming pool or something, you estimate its depth, and you underestimate how deep it is because of this refraction effect. Or my favorite example of this is going to those tropical fish stores and walking around the aquariums. And as you walk around the aquariums, some fish just disappear because of this refraction effect of the light coming from through the water into the glass, into the air. The light gets bent, and the images that you see just shift back and forth as you kind of change your angle of view. Here is the formula that relates all this. So we haven't done a detailed derivation, but what we're going to say is theta 1, the angle of refraction on one side, and then the angle of refraction on the other side. Yeah, here we go. Theta 1, let's say the angle of the incident light, and theta 2, the angle of the refracted light, are related through N1 and N2. The specific relationship depends on the sign of theta 1 and theta 2. And if anybody's interested in seeing a derivation, it's not too terribly involved, but stop by office hours and we'll take a look at that. So let's try this. Let's take some light coming in this direction. We're going to draw the normal. It's going to refract. Now it's also going to reflect, but we're ignoring reflections for now. So the incident angle is 60 degrees. Now it's going into glass. Glass is going to have a higher index of refraction. The photons of light are going to interact with these glass molecules more. That's going to slow them down. And so we're going to have a different angle here. Now this glass block that they've given us has two surfaces, two refractive surfaces we have to consider, but they're parallel. So whatever angle theta A is here, we're going to get the same theta A here, and then we'll get the same angle on exit. So just from the diagram, if this surface and this surface, if they're really parallel to each other, then theta B equals 60 degrees. Okay, that was not a difficult problem. But what about theta A? So let's take a look at some numbers. It says the glass index is 1.50. For the air, we'll probably just use 1.00. We don't have to use 1.0003. What is theta A? We've answered part B, I think. Let's see what this problem looks like. So I've drawn a careful diagram. You can tell I've used a ruler, because careful diagrams help make the problem more clear. They just really do. If you don't have a clear ruler that you can work from to draw these diagrams, get one. So here's the index here, and the index on the other side. Theta 1 and theta 2. Theta 1 is 60, N1 is 1, N2 is 1.50. I'm using this formula, there's the formula relating the refraction effect between the two materials. And so sine theta 2 is going to equal N1 over N2 times the sine of theta 1. I put all the numbers in. I get 35.3. Now at this point, you need to check your numbers. For whatever reason, it's really easy to get the N1s and the N2s mixed up. Like, maybe I get these numbers reversed here. So even before I start doing the calculations, I'm saying that's 60 degrees. The glass is optically more dense than air. Therefore, theta 2 has to be less than theta 1. So I look, and yeah, it's less, and it's significantly less, and I'm kind of expecting that, and I think the 35.3 degrees is a good number. Now, another thing that comes up is make sure that your calculator is set to degrees. Physics is one of those classes where, maybe the class, where you've got to make sure that your calculator is set to the units that you're actually measuring the angles in. There are going to be instances where we're using radians. So we will be using radians, specifically chapters 34, 35, when we look at kind of the quantum effects of light. Right now we're just using degrees, but make sure you know which angles are being put in, which units are being put in. So if theta 2 is 35, then from the geometry I can say that these interior angles, they're going to have the same value. So theta 3 equals theta 2, and we already solved for theta 4. Okay, but that's a nice example to start from. That's a very kind problem. It's showing us some good things, and we can use a little geometry for it. Now, let's talk a little bit about properties of light. We're kind of interested in doing this. So we've looked at refraction. I was thinking we had another example. Maybe we don't. Okay, so definitely look at the homework problems for refraction. You want to get more practice with refraction. All the mirror stuff is important. All the refraction stuff is also really important. Those are going to be the top items in the chapter. So make sure you're good on both. And again, it looks like maybe this is our only example from lecture, but I know there's more homework problems and more in the textbook. All right, let's just start talking about light itself and some of the properties. Light consists of particles, and we call those particles photons. Photons are massless, and it turns out that massless particles are always traveling right at c, where c is the speed of light. And as we talked about in some earlier chapters, C is actually telling us how space and time are connected. And so special relativity predicts that, first of all, it says there's no problem with not having mass. A lot of physics, a lot of the physics that we've studied so far, might lead you to think an object has to have mass if it's going to exist. But special relativity says no, it doesn't. Okay, you can have particles that are massless, no big deal. And photons are the first example of particles that we're going to encounter that they don't have mass, but they certainly exist. Light exists. So they don't have mass, and any particle with no mass is always traveling at c. So these photons are always traveling at that speed. Now, in addition to not having any mass and traveling at c, photons, like other particles, just like electrons or protons or neutrons or neutrinos, photons have energy. They carry around a certain amount of energy with them. It's variable. You can have high energy photons or low energy photons or photons with medium amounts of energy. So photons will have energy. They also have momentum. Now we saw some of this in the previous chapter where we were kind of doing the transition. That was kind of wrapping things up with electric and magnetic fields and then introducing that as properties of light or properties of photons, the particles that make up light. So these particles have energy, they have momentum, they have angular momentum. Photons have spin, just like electrons do, if you've seen that in maybe your chemistry classes. So the fundamental particles that we work with, they all have a certain amount of angular momentum that they carry around with them. And photons are not an exception to that. All right, so let's see what are the range of energies that the photons can have. Now back in chapters, I want to say like chapter 23, we introduced energy units that were called EV. And we said they're not standard, but instead of using joules to write down the energy of individual photons or electrons or such, it's easier to use this different unit. And especially it's easy when we look at the visible part of the spectrum of light. Our eyes are sensitive to photons with energies between about 3.10 EV to about 1.77. So that's the range of energies that activate the rhodopsin protein/embedded molecules in your retina. The photons have to be within that range, otherwise you don't see them. You don't experience them, they don't set off neurons that result in visual experience. Now, in terms of the wavelengths of the light, that runs from about 700 nanometers to 400. Now, I always see these charts that disagree a little bit. A lot of charts just cut off at 700 and say that's it. Other charts show that our vision goes to 750. I'm not sure about the details on that. But more often than not, what we will be thinking in terms of is that human vision, the human retina, is able to pick up visual photon energies or photon wavelengths between 400 and 700, photon energies between 3.10 and 1.77. Those are often the numbers that we'll be working with. And then there's this nice view of what the different energy photons, how we experience them. So, all the different colors, whatever the experience of color is, we can trace that back to the energy of the photons that have activated our, the cones in the retina, I guess. We have different types of cones that are sensitive to different parts of the spectrum, and that's combining those, processing that information, is how we experience color. What this is showing is that the index of refraction actually varies in a material. So we've been treating this as if, hey, if it's glass, the index of refraction for this glass is 1.5, and that applies for the whole spectrum. And that's not quite true. What we find is that, let's say that we take the entire spectrum of visible light. Well, when all parts of the visible spectrum are present, we experience that as white light. But when we take all those different energy photons and send them through, say, a piece of glass and refract them, what we're seeing here, for example, is that the violet is refracting more than the blue, which is refracting more than the green, more than the yellow. So you can see that there's a rainbow effect. And rainbows are another example of this. So this is actually scattering of the, or refraction of the light through water droplets in the air. So rainbows occur, not necessarily during a rainstorm, but when there are still residual water droplets away from us in a region of the sky, and the light passing through refracts, the sunlight refracts and actually reflects and comes back. And the different energy photons refract differently, and that separates them. And so when the light exits, we have created what's called dispersion. The light doesn't all follow the same path. There we go, there's the rainbow. And here is the diagram. So what happens is, here is sunlight coming in towards these water droplets. You get a refraction at the front surface, a reflection at the back, and a refraction at the front surface again. Now that's not all the light. Some of the light reflects here and some of the light goes out the back, but the specific path through the raindrops that result in the rainbow effect is refraction at the front, reflection at the back, refraction at the front. And because of the difference of how much the different, violet photons interact with those water molecules more. And so the refraction angle is greater, and, or the refraction angle is, yeah, so there's a greater effect of refraction. The actual theta 2 becomes less. So the refracted angle is less, that creates a bigger effect, and it creates dispersion. So we end up with the different energy photons coming away from that raindrop, away from that field of raindrops, at different angles, and that creates the effect of a rainbow. Pretty cool. And I know you guys probably know you can create your own rainbows. Let's see, if the sunlight is coming from here, then what I want to do is turn around and get my garden hose and spray water droplets in the air with the sunlight at the back behind me, so that the sunlight can go in and refract, reflect, refract, and come back towards me, and then you can see that rainbow effect. Okay. There's an effect with refraction also. It's called total internal reflection. And let's take a look and see what that is. If we start with light coming from an index that's higher, so here we have a material with a higher index of refraction, and that's the water, going into the air, then the angle over here, theta 2, is going to be bigger than theta 1. And as theta 1 goes up, as we look at different angles here, theta 1's getting bigger. Well, theta 2 is getting bigger faster. And at some point, theta 2 hits 90 degrees. Once I exceed picture K, once I go on to picture L, at picture K we say we are at critical angle. We are at the point where if theta 1 gets any bigger, refraction will stop. There will be no light passing into the other material. That's kind of remarkable. What it's saying is the light is totally reflected within the material. The light can't escape if it strikes the surface at an angle larger than the critical angle. And it's easy enough to get a formula for this. What we say is if we are at critical angle, then theta 2 has gone to 90 degrees. That's the limit. And if we use the law of refraction, what that tells us is that, following that formula, the critical angle is equal, the sine of the critical angle is n2 over n1. For a water-air boundary, that would be, the sine of the critical angle is 1.00 divided by 1.33. That's the index of air divided by the index of water. It says if the water strikes, if the light strikes the water-air boundary coming in from the water at an angle larger than 48.8 degrees, the light totally reflects inside the water. It can't escape. The light will not exit. And so that creates these effects. If you've ever done this, this is a really cool thing to try out, is get some goggles. Get some goggles. Get some goggles and then get something, hold your nose or something, take a breath, drop below the water, and then look straight up. Again, hold your nose, otherwise your nose kind of floods with water from the pool. And what happens is, because of refraction, the entire 90 degrees horizon here and 90-degree horizon here is collapsed within that critical angle of 48.8 degrees. And so it's a cool effect if you've got, well, this is what they're showing, right? If you've got these trees out to the side, and you don't have to go to the tropics where there are palm trees, but that's what it's going to look like, right? So what will happen is there will be this cone of 49 degrees, and everything from outside has collapsed into that. Really cool effect. Another interesting effect with this total internal reflection is that, like in a really nice set of binoculars, instead of using mirrors inside there, they actually use glass. So they're going to use a dense glass. If you can get a dense glass where the critical angle is less than 45 degrees, and that's not difficult, then what you can do is, if this is a block of glass, and the light comes in through the binocular, well, it's going to pass right through that first surface, because it's at 0 degrees, but it's going to hit this surface at 45, and it totally internally reflects. So it undergoes total internal reflection again, again. How much of the light can we get to follow that path? Basically 100%. So total internal reflection works really, really well for these kind of circumstances. Also for optical cables, for transmission of information. How can I get a fiber optics cable to contain light? Because with fiber optics, we're not using electrons. We're not using a current of electrons. We're using a current of light. A bunch of photons. We're using a current of photons. And as long as we make sure that the light is directed along the length, when the light does bounce off these surfaces, as long as it's past that critical angle, it totally reflects internal to the glass, which is what the fiber optics cable is made out of. Okay, last topic. Now this is a bit of a tricky topic. We're going to look at one example, but what we're going to say is, we looked at mirrors, and we did a bunch of examples with mirrors. Mirrors were an example of one surface reflecting the light. Now in the next chapter, we're going to look at lenses. Lenses are actually two surfaces. There's a front surface and there's a back, and that is based on refraction. And we've looked at refraction now, so we're ready for the next chapter. But there's something in between that we want to talk about, and that is, well, what if you just have one refractive surface? And so for that, what we can do is come up with a general formula. Again, the derivation here is a bit complicated, but what we're going to say is, let's say we have an object, and it's located an object distance away from a single refractive surface. So we're going to go from something that has an index of n1 to something that has an index of n2. And here is one of those possible paths of light. And when it gets to here, it's going into something denser. Theta 1 is the angle that it strikes the surface at. Theta 2 will be the angle that it passes into the next material. And as you can see, this is creating a converging effect for the particular values of this problem. It's showing an example where that effect is converging and it forms an image inside. Now when we do the careful analysis of this, let's take a look at a couple of examples of using this. One example would be this. Let's say that we have an object that is down on the surface of a swimming pool. So it's down on the bottom of a swimming pool. And where is its image going to show up? And so what we can do is we can say, okay, the light from this is going to spread out. It's going to reach this front surface, and then it's going to refract away. So that suggests to us that what's going to happen is the object light is spreading out as it approaches the air, and then the refraction is going to bend. The light coming out is going to appear to come from a closer location. This is that effect that we were talking about before, where you look at the bottom of a swimming pool or something, and you look at the tiles and the pattern, and it looks closer than it really is. You jump in and you find out that the pool's deeper, significantly deeper than you thought it was. Now this is the formula. If we go back to that previous diagram that we just had here, that one, when we do all the analysis here and we look at the DOs and the DIs and the N1s and the N2s, the formula that we get is N1 over DO plus N2 over DI is equal to N2 minus N1 over the radius of curvature. That's different from the formula we've been using for mirrors, and it's different from the formula we'll be using for lenses. This one's actually a little more complicated because it has both indexes of refraction that it has to deal with. So it looks kind of like that formula, and what we have is a 1 that's been replaced with the index of refraction for that material. And then we have a 1 that's been replaced by N2, the index of refraction of the second material. And then instead of 1 over the focal length, we have N2 minus N1 over the radius of curvature. Now for the example at hand, for a flat surface, the radius of curvature is infinite. And so I can write down the N2s and the N1s. If it is a flat surface, if it's planar, then this last term, because the R is infinitely large, that becomes 0. And so that says that DI is minus DO, N2 over N1. Plugging all the values in, it predicts minus 75 centimeters. And that works. Let's see, oh, here it is. The DO is 1 meter, and that's right here. So the DO is measured, this is where the boundary is between the materials. And so I'm coming back from that boundary. There's a real object with light spreading out, and it's located, here it is, I got the DO. So measuring back from the boundary to where the object is located, that's 1 meter, 100 centimeters. And this is telling me that the DI will be negative, so it's going to be virtual, and it's going to be right there. It's going to be at the 75 centimeter mark. So yeah, it seems about right with that effect. Now, that's a good example. Here's another example. This one's a little trickier, but let's take a look and see. Here is the location of an image. And what we're going to do is we're going to let light from this pass through a spherical piece of glass, right? Yeah, glass sphere. We're going to get a refraction here and a refraction here. And then we'll see if we get an image set up or not. So we're going to see if this leads to the formation of a real image or if the image is going to be virtual. So what they've told us is that the radius of our glass sphere, we're going to set that at 10 centimeters. And then, oh, I'm sorry, that's not the source, that's image 1. So let me go back. This is where the object is. So the object is located here. Okay, so object is here, and then the object comes up and it refracts at the front surface. When it refracts, it appears the light is coming from image number 1. So we can talk about the image that's formed at a single refractive surface. Now I can take that image and treat it as an object. Image number 1 becomes object number 2 for this surface. So as far as this surface is concerned, the light's coming in along here. It's as if it's coming from that point out there. That is image 1 and object 2. And then it will refract, and then we'll get image 2 from that. So that's what the setup looks like. So it looks like for 2 surfaces, we have to use that formula twice. Okay, and the formula is right here, so that we don't lose track of that looking to see if I wrote it down anywhere else. So the formula is right here, same formula that we used before. I've moved one of the terms over. But N1 is 1, so this is refraction at the front surface. What we're told in the example, or what we... Did they tell us this, or did I... Yeah, 25 centimeters, okay, from the center. Okay, here we go. So what they told us is if we measure from the center of the glass sphere, we measure out 25 centimeters, that's where the object is placed. Now, we're going to assume that the formulas we're working with, we're going to assume we're going to be looking at small angles. So we're really thinking of light that reaches this region at the front. So that distance right there is going to be 15 centimeters. And so DO becomes 25 minus 10 is 15. The radius is 10. Plugging all of those numbers in gives us an image distance of minus 90, which kind of looks like that drawing that we had. So let's go back and look at this. So what they're saying is, check the numbers here. This is 10 centimeters. This was 15, right? The whole distance here was 25, so this is 15. And then from here out to I1 is 90 centimeters. Now, if that's 90 centimeters, then when we move on to the second surface, we have to add on 20 centimeters. That's the diameter of the glass sphere. So what we're going to do is say that DO for surface number 2 is 90 centimeters plus 20. That's going to be 110. And it looks like it took me a few tries to get this right. N1 in this case is 1.5, and then we're exiting back out into 1.00. Again, writing this formula down, carefully putting everything in, carefully calculating everything, keeping track of all the signs. I ended up with a DI, there it is. The DI worked out to be plus 27.5. Now that's going to be measured from here back out to here. So those values are measured from the second surface, which is here. The first set of values are measured from the first surface, which is here. Now what's going to happen with this glass sphere, this would be really cool to play around with too, is that again, what we're imagining is most of the light that's going to form our image actually is going to come from a fairly narrow band in this region. So we're using kind of this small angle approximation to see what's going on. I would be very curious to see, with this setup, if the image is really sharp or if it's a little fuzzy. Because if we do end up including these regions out here, it could turn out to be kind of fuzzy. What we could do is we could take this glass sphere, take this well-illuminated object, and then put some kind of a barrier here so the only light coming into the sphere is limited to a narrow region. I think that's going to sharpen the image. But this would be a really interesting. So if any of you guys have a 20 centimeter perfectly spherical piece of glass, bring it in and we'll play around with it and see if we can create this effect. See if we can get the measurements to match up with what we've predicted here. So I think that puts us at the end of the chapter. I hope this is pretty interesting. It's kind of new. It's different from what we've been doing, right? We're using a lot of geometry here. We're thinking about light, which we have a different sort of intuition for compared with the electric and magnetic stuff that we had been looking at. Again, those are kind of the go-to equations. Those are going to work with mirrors and lenses. And then there's that one last problem at the end of the chapter, that one set, those examples at the end with a single refractive surface. So don't forget about these guys. Okay, if there's any questions, which I'm sure there are, stop by office hours. Let's get those looked at. And we will get a good start on this geometric optics.